So before I begin this video, please remember that I'm writing these videos as fast as I possibly can, and they are not really being edited. So you're going to hear a lot of smacks, a lot of mistakes. There's going to be a lot of places where the film doesn't quite sync up. Just, please be generous. This first video is on sequences and on series. I'm going to give you a motivation for why you would want to study such a thing. So our problem is that functions are really great, but they have often very difficult antiderivatives, and therefore we can't use the fundamental theorem of calculus to find our definite integrals. And others, if you take multiple or higher order derivatives of certain functions, they become insanely complicated. So we want to fix that. In many cases, the idea is to approximate the function with a polynomial of a specified degree. By then increasing the degree, we hope that we increase the accuracy of the approximation. So here is Desmos, and you'll notice that I'm using the function e to the x squared divided by 100, as this is a function we mentioned just moments before as a function that's very hard to find its antiderivative. Now these particular functions that you see here, polynomials, would all be good approximations to this particular function. So if you want to define the area under the curve of the function e to the x squared divided by 100 over the interval from 2 to 14, the shaded area here is the area that I need to find. Now if I go and start using the approximations, you'll notice that by using the polynomial just constant 1, there's a great difference between this bluish purplish area and the pink. But by increasing the degree of the polynomial from 2 to 4 to 6, and then I didn't even put down the others, 8, 10, and 12, you'll notice that the approximation gets incredibly good. Now there's something else here that I want you to notice, and that is if you go and look at this on a point-by-point basis, notice that for this 1x value, that this is the first approximation. This y value of 1 is our approximation to the function's value of 2.718. And by going and increasing the degree, notice that for that 1x value, the polynomials approximate the function's value closer and closer until you can't tell the difference anymore. There's a feeling then that I can increase the polynomial degree, and by doing so, I can increase the approximation, at least for this function. You might also notice that in each case, the polynomial is compared to the one preceding to it by just adding on one more term. So these polynomials must have some kind of pattern to build them. Now, in order to go and discuss this topic in a more general sense, we need to first discuss what happens right here. As I'm looking at a single fixed x value, these polynomial values are all approaching a single value. So we need to have a feeling for, as we increase the number of steps, what happens to the corresponding values, and what do we mean by that those values approach another value. So let's begin with that idea. We'll start with the definition of a sequence. All sequence are is just a bunch of numbers in an infinite succession called terms that make some kind of infinite list. So for example, 1, 3, and 5. The terms in a sequence are usually denoted with a lowercase letter and a subscript. Now, for convenience, the first number in the list is called the first term and often is associated with a subscript of 1. So, for example, if I were to say this is the sequence a sub n, then the first term would be a sub 1, and that's 1. A sub 2 would be 3. We could then express a sequence often as a function of n whose domain is in the integers that are greater than or equal to 1. So the sequence a sub n equals 2 to the n minus 1, where n goes from 1, 2, and 3, that would generate the sequence a sub 1, a sub 2, a sub 3, and just by plugging in 1 and 2 and 3 into the function, you get the values of 1, 3, and 5, the sequence that we saw just moments before. Now, just to give some names to these terms, if you ever see a sub n, that's called the nth term of the sequence. And from now on, now notice there's a couple problems with this. And the main one is that a sequence of numbers can actually have many representations. The easiest one is that you can just replace the index variable with another variable. That doesn't change it substantially. But you could change the domain of the index and then use a modified function and still have the same sequence. So for now on, we'll just say that two functions represent the exact same sequence if they generate the same numbers in the same order. For example, a sub n equals 2 to the n minus 1, where n goes from 1, 2, and 3. And the sequence b sub n equals 2 to the n minus 5, for n equals 3, 4, and 5. These actually both generate the sequence 1, 3, and 5, and so on. Now, integers then free us from using certain type of functions. We can now actually use more operations. The two most common that you see for sequences is called the factorial, n with an exclamation point. It's defined for all non-negative integers. And we define 0 factorial as 1. 3 factorial would then be the product of all the integers from 1 to 3. And n factorial means the product of all the integers from 1 to n inclusive. Now, if you see negative 1 to the n, we can now use that also in our functions. And it represents a way to create an oscillating sign change. Now, you need to have a little bit of practice with factorials because you're going to see them quite a bit. So let's go ahead and by hand evaluate 7 factorial divided by 3 factorial. You could, if you want, rewrite each one in terms of what they equal. 7 times 6 times 5 times 4 all the way down to 1 for 7 factorial. And 3 factorial could be replaced with 3 times 2 times 1. Then the common factors of 3, 2, and 1 would cancel, leaving you behind the products 7 times 6 times 5 times 4, and that's 840. This is a way to go about doing it. It's really not a good idea, though, because it's fairly inefficient. Let's do the same thing, but using some algebra instead. Now, 7 factorial has inside it the multiplication of 3 times 2 times 1, but that's 3 factorial. So I won't write down 3 times 2 times 1 when I expand the value of 7 factorial by its definition. I'll just replace the 3 times 2y times 1 and put 3 factorial in its place. So 7 factorial then would then be the same as writing 7 times 6 times 5 times 4 times 3 factorial. And the denominator, I won't even expand out. It's just 3 factorial. That way the 3 factorials cancel, leaving you still with 7 times 6 times 5 times 4. And that's still 840. You can, of course, if you want, go use your calculator to evaluate these expressions. But once again, this is a fairly bad idea because factorial grows really fast. And if you type in like 80 factorial or 100 factorial, it will probably just crash your calculator as it just can't handle it. It just gets too large too fast. Now, you're going to need to do the exact same thing with variables. So let's try one. If you see n factorial divided by n plus 2 factorial, now think when you expand n plus 2 factorial, the first term is n plus 2 times 1 integer less. So then if you start with n plus 2 and go 1 integer less, that would be represented by n plus 1. And the next integer below that would be n. The next integer below that is n minus 1 and so forth. But at some point, I want to write the rest of it as a factorial. Since the numerator is a n factorial, I will write the denominator as n plus 2 times n plus 1 times the remaining integers I didn't mention, which was n factorial. That means then we could then cancel the n factorials, giving us the resulting fraction of 1 over n plus 2 times n plus 1. Now, they can be a little tricky, so let's just do that exact same thing again. If you have 2n minus 1 factorial divided by 2n plus 1 factorial, now, if you think about the denominator, 2n plus 1 is an integer. You want to get 1 less. So if you have 2n plus 1 and go 1 less, being 1 less, it would be 2n. Going 1 less, it would then be 2n minus 1, and so on. So I will write the denominator as 2n plus 1 times 2n times the remaining terms, which happens to be then 2n minus 1 factorial. Then those factorial. Now, you might want to graph your sequence to see what it looks like. So if you wanted to graph the sequence a sub n equals the cosine of n over n, you could on a TIA 384. I'll show you how it's done. If you go to your mode, you could then change the fourth row from function mode, which is the normal mode, that's f of x equals or y equals, into sequence mode. When you do so, you'll get the screen below. You'll then get n min equals 1, which just tells you basically the first n value that you're allowed to use in your particular sequence. It's a way to define your domain. And then u sub n is, and then you define your function, cosine of n divided by n. Your x theta t button now will be n on your calculator instead. Now, if you just type in your function, that's it, you won't be able to see anything. So you need to set your window in such a way so you can see it. By pushing the window button, you'll notice it's also different. You'll now have a n min and an n max that then tells you the range of n values that it will graph. You have to tell the plot start and the plot step. That way it knows how to skip from n to n. You have to give it the normal range, though, too, for your x range and your y range. Think of x range as being the n range. So x should really start at 0, and then just make it be fairly large, say 10, 20. And then the x scale, again, go by ones to make it easy for you. So you can see this increase, the steady increase in the input as it goes over the integers. The y range, though, you don't really know, and you have to sort of just guess. You can always use a zoom setting once you set the x range. Zoom fit, I believe, will then, once you give it the x range, it will automatically figure out a y range based upon your function values. Just make sure that your n max is at least as large as x max, or it'll plot a bunch of points. It will then stop, and you'll have a whole lot more window with no points in it. Now, you might wonder then, what would it mean then to have a limit of a sequence? After all, that's why we're doing this. So there's a couple versions. The simplest version is if every open interval containing L contains all but a finite number of terms of the sequence, then L has to be the limit of the sequence. Now, in that case, we would write that the limit of a sub n, the limit of the sequence, as n increases without bound, as n goes to infinity, is L. But a more formal way of saying the same thing is, a sequence has a limit L if for every epsilon there is an associated integer n, such that the difference between the sequence value and the limit, that the difference is no more than epsilon. And that's true for all n, all values of the index greater than some sort of bound. It means then that it's more like the sequence approaches a single number. If you think of it on a number line, if the sequence has a limit, we'll say the sequence converges to L. We often just will say the sequence converges because sometimes we don't care what it converges to. Otherwise, if the limit doesn't exist, we'll just say the sequence diverges. So for example, let's suppose that we have a sequence, a sub n, that's converging to L. I put L on the number line, and here will then be the interval that I want the sequence to be in after a certain point. And notice, here's my sequence. After you get to a certain point, all the sequence... Let's go ahead and look at a few examples. So here's the sequence you saw before, the cosine of n equals n. And I've provided the graph for you. So now if you look at the graph and you look left to right, you'll see that the points, those y values are the sequence values. The x coordinate is the index value for that sequence. So a sub 1, a sub 2, a sub 3, they seem to vary a lot away from, it looks like, the x-axis. But as you go to the right, notice how the function values vary less and less and less, and they all uniformly approach a single value. They appear to approach 0. So you would say that the sequence, at least by evidence, it seems the sequence here converges to 0. You would say the limit of the cosine of n over n as n increases with a bound is 0. Doing the same thing, if you look at the sequence of a sub n equals 1 minus 1 over n squared, once again I've given you a graph. If you look from left to right, you can see that the sequence values vary up and down, but as the n increases, the output varies less and less, and it appears that the values of the sequence all approach, or get as close as we'd like to at least, the value of 1. So you would say the sequence a sub n converges to 1. Now here's an example of a diverging sequence. If you look at the sequence a sub n equals 2 plus negative 1 to the n, as n goes from 1 to 2 to 3 to 4, the values of a sub n go from 1 to 3 over and over and over again forever. They don't approach anything. The sequence in this case just diverges, and the limit, in fact, just doesn't exist. We can't say anything about it. But on the other hand, I didn't graph this one. If you look at the sequence a sub n equals n squared, then in that case, of course, as n gets large, n squared gets really large too. So the sequence diverges for sure, because there's no limit value. But you can say this time that the limit of n squared, as n increases without bound, would be infinite. Now, given a sequence, its convergence depends solely on whether the limit exists. So if we say the sequence converges to L, that's the same as saying the limit of the sequence exists, and that limit is L. If we say the sequence diverges, that's the same as saying that the limit of the sequence just does not. Now, given a sequence a sub n, this sequence converges depends solely on whether the limit exists. So we say that a sequence converges to L if and only if the limit of the sequence exists, and that limit's L. If the sequence diverges, then that means that the limit of the sequence just doesn't exist. Now, since sequences are functions with domains that are restricted to just the positive integers, many of the limit laws I taught you way back when in Calc 1, they all still apply. So the next few slides go through a few. Prepare for a really large wall of text. So as a big theorem, you'll probably recognize this. If you're given two converging sequences, a sub n and b sub n, and any real number k, the sum, a sub n plus b sub n, the difference, a sub n minus b sub n, the product, a sub n b sub n, and the constant multiple, k times a sub n, are all convergent sequences. And the limit of the sum is the sum of limits. The limit of the difference is the difference of limits. The limit of the product is the product of limits. The limit of the constant multiple is a constant multiple of limits. You probably have heard me say that before. The same thing we've heard before if you take the quotient of two sequences, doing it term by term to get a new sequence. This new sequence will converge provided that the sequence in the denominator is actually never 0. Because when you create this new sequence, you evaluate the sequence a sub n and b sub n for a choice of n, and then divide them. Well, that b sub n then can't be 0 ever, because if it is 0, then a sub n divided by b sub n for that choice of n wouldn't exist, and we couldn't define the sequence in the first place. So the denominator sequence can never be 0 for the choices of n we're using. Also, here are two other little techniques that we can use. Now, if you're given a sequence a sub n that happens to converge to L, and any other function whose domain includes all the terms in the sequence so that you can evaluate the function at those values, and actually the function is also continuous at L itself, then the sequence that's created when you evaluate the function to each term in the sequence. So you take the sequence and evaluate the function for each of those values. That makes a new sequence. This would then actually also converge. And in fact, the limit of this new sequence is the same as taking the function and just taking the limit of the original sequence. It's as if the limit and the function evaluation can be swapped. Now, that was one of the results of continuity way back when. This is just the sequence version of the same thing. Another good example of something you've seen before that now we're going to use quite a bit more is the squeeze theorem. So if you have two sequences, A sub n and B sub n, that are both converging to L, and you have another sequence, C sub n, so that at every choice of n, the new sequence, C sub n, is between the values of the other two sequences, then since the outer sequences are converging to L, the inner sequence, C sub n, will also have to converge to L.
So let's go ahead and look at this particular example on how to go about applying the limit laws to find the limit of this particular sequence. Now, the techniques we use here are very identical to what you saw way back in early Calc 1 when you were finding limits as the input was approaching infinity. So for example, in this case, to find the limit of this particular fraction, you can separate the numerator and the denominator. By doing so, dividing the n squared into 4n squared and dividing n squared into 1, you convert the expression into an equivalent expression of 4 plus 1 over n squared. That particular limit is very easy to do because you can then apply the sum limit law, that the limit of the first term plus the limit of the second term is the limit of the original function. And you all know the limit of 4 as n increases without bound is just 4. And the limit of 1 over n squared as n increases without bound, that limit is also 0. So the limit then is 4 plus 0, which is 4. So the sequence 4n squared plus 1 divided by the quantity n squared, that approaches the value of 4 as n increases without a bound. Similarly, suppose you wanted to find the limit of this particular sequence. Once again, it's very, very similar to what you saw before in Calc 1. If you need to, though, notice that if n were to increase without bound, 5 times n would also go to infinity, and the denominator, n squared plus n, if n is going to infinity, n squared goes to infinity, n goes to infinity, their sum is then going to increase without bound, going to infinity, and the square root then does the same thing. So this particular fraction, if n increases without bound, is of the form of infinity over infinity. Now, that's an indeterminate form. Most students will then try L'Hopital's rule. This particular fraction that was set up that if you try L'Hopital's rule, that it won't ever get anywhere. So it's better to use the old techniques first. In this case, to find the limit of this sequence, notice that in the denominator, the fastest growing term, taking into account really all the major operations of multiplication, division, and roots, would be the square root of n squared. That's n. So I'm going to divide the numerator and denominator by n. Now, in the numerator, 5n divided by n, that's just 5. In the denominator, though, I can't simplify the square root of something over n. I need to convert the n into something that has a square root in it. So you convert the n to be the square root of n squared. That way, when you're dividing two radicals with the same root, you can use a single radical and just divide the radicands. So then on the next line, I just do so. I turn that division of two radicals as a radical of a division. You can then take the n squared, divide it into n squared plus n, and to separate that fraction, like in the previous example, to get this expression. And now the limit is easily done. Because the limit of 5 is 5, the limit of a square root is a square root of a limit. The limit of 1 plus 1 over n is the limit of 1 plus the limit of 1 over n. And the limit of 1 over n is 0, and the limit of 1 is just 1. So you get then just the fraction 5 divided by the square root of 1 plus 0, which is just 5. So the sequence then approaches the value of 5 as n increases without bound.
Let's try one more. So let's determine if this sequence, negative 1 to the n over n squared, if that converges or diverges. To do that, it's going to be a little more difficult because of the negative 1 to the n. We don't really have good techniques that I developed in Calc 1 to handle that. At least we didn't mention it too often. So here, notice that if you were to look at the sequence negative 1 to the n, it's either 1 or negative 1. So I'll look at two different sequences. I'll look at one sequence where the numerator is just 1, and another one where the numerator is just negative 1. In each case, the limit of 1 over n squared and the limit of negative 1 over n squared as n increases without bound, those limits are 0. Also notice that negative 1 to the n over n squared is always between, actually is equal to, one of those two sequence values for every single n. Negative 1 to the n over n squared is actually either equal to 1 over n squared or equal to negative 1 over n squared. The only thing that matters is n even or is n odd. If it's even, then it's equal to the one on the right. If it's odd, then it's equal to the one on the left. So by the squeeze theorem, I can then say that the limit of negative 1 to the n over n squared. We have two more ways to go about investigating whether a sequence converges or diverges. Take, for example, the sequence a sub n equals natural log of n over 2n. Now, the previous techniques I just gave you will not work. But what we can do is that you can notice that if we replace the n with an x and shift the domain, instead of being from only integers to being all reals from 1 and up, notice in that case, we can now use L'Hopital's rule because the natural log of x then would be defined for all real numbers, and that's a differentiable function. Since the limit of the natural log of x over 2x equals, by L'Hopital's rule, the limit of 1 over x over 2, and that limit's 0, and since the function, the natural log of x over 2x over the interval from 1 to infinity, is just a natural continuous extension of the sequence of the natural log of n over 2n, you could then say that the limit of the natural log of n over 2n equals 0. Now, there's plenty of people that will just say, why do we change the x at all? Why don't we just take the derivative in terms of n? And you know what? There's a lot of people, especially those who are just trying to get a quick, dirty answer, that will do just that and never even replace the n with an x. But you should notice, though, that if you're being careful, that if the domain is only integers, 1, 2, 3, and so forth, you can't take a derivative of a function like that because you can't have a small enough change in input. If the change in input is always 1, you can't get smaller. So you actually can't. All right, so the very last trick about sequences. This last one is a little bit unsatisfactory to most students because it doesn't tell you how to find out if the sequence does converge, what it converges to. To build up to this really nice theorem, we need to define a few more terms. We say a sequence is bounded if, for some real b, that the values of the sequence are trapped by that value. It's just a fancy mathematical way of saying that the values of the sequence never get too low and never get too large. They're between two numbers always. A sequence is called non-increasing if the next value, a sub n plus 1, is always less than or equal to the previous value, a sub n. That means then that the sequence can never increase. If a sequence is called non-decreasing, that means the next value, a sub n plus 1, is always greater than or equal to the previous one, a sub n. So then if the next value is always greater than or equal to the previous value, it can never decrease. It's either the same value or it's more. We say a sequence is monotonic if it's either non-increasing or it's non-decreasing. The big bad theorem is called the bounded and monotonic convergence theorem, and it says if a sequence is bounded and it's monotonic, then it converges. So it's really nice that it converges, but it's not that great because we don't know what it converges to. But as you've seen before, in Calc 1. Now, this particular theorem is confusing enough, and the conditions are, well, frankly, kind of hard to establish for most students, that it's going to be pretty much reserved to me using it and not you. You should know about it, but you won't have very many opportunities at all to ever use it. So, but if there's anyone in the room who really wants to know, I will make another video of about 5 or 6 slides where I go through one problem to show you what it's like. And even then, I won't go through all of it because I'm not going to be teaching you in. And that gives you a very brief introduction to sequences. The next video, next class, we'll talk about series and how they're connected to sequences.